Okay, thank you very much. TNO, you might know us from the TNO multi-energy model, but TNO was also the organization behind the colored books, the yellow books, and that's from the department where I'm from, industrial safety. I'm going to talk about geographical societal risk. Rest assured, it's not a new criteria, it's just a visualization method aimed by improving understanding of societal risk. And it has all to do with the typical Dutch situation and the way the legislation is over there. I'm going to give you a brief introduction about safety legislation in the Netherlands and more specific, the usage of risk assessment even during urban development planning, because that is actually what is occurring in the Netherlands. I'm going to get you through the concepts of societal risk maps and explain a bit about different types of societal risk maps that you can draw, and explain what do you see and why they are created and why they are used and how they are being constructed. They were developed a couple of years ago, and last years we have some nice experiences with practical applications of these maps in probably not too nice situations, but it clearly indicates the use of the maps. Give you some conclusion and evaluation and room for questions. Some background about safety legislation in the Netherlands, and coming from the Netherlands, I'm aware of the fact that you often see our country as the country of the tulips, or perhaps the country of the cows behind the dikes who are below sea level, or even the country of the windmills. Unfortunately, that's not the whole truth. We are a country with 70 million people, and compared to Texas is 20 million people, but Texas is 20 times as big as the Netherlands. To make matters worse, 75% of the population is concentrated in the western area, where cities like Amsterdam, The Hague, Rotterdam are growing together into one big metropole, including all the problems you can realize in that typical situation. So we have traffic jams, we have shortage of housing, we have crowded areas, and you can imagine we have a lot of industry in this western side of the country as well. And this industry is really very close to the population. The Netherlands, they often refer themselves as being the distributing center of Europe. So we have a large harbor, Rotterdam. But it also brings a lot of transportation through the country, to Germany, through France, to Belgium. We have a lot of refinery in the harbor area and in industrialized zones. So that really also includes problems related to safety. So having these densely populated areas close to industrial sites, you can imagine that requires a strict regulation, and that is exactly what has been happening. Already in the 70s, these colored books, as we refer to them, were developed. They are basically typical guidelines, a bit like you do here with the CCPS guidelines on how to perform a consequence analysis or how to do a QRA. Currently, every risky company in the Netherlands, so involving large amounts of dangerous chemicals, is required to perform a safety report. That safety report should contain a QRA. That's the only way you can get a license to operate. So a lot of QRAs have been and are being performed in the Netherlands. But on the other hand, as soon as a company has a license to operate, we have a city who wants to expand and is asking, well, can I expand? Can I build houses over there without offending the license that he has and exceeding the criteria that are set? So risk assessment is also used during urban development planning in the Netherlands, and that's quite a typical situation, I think. There's not so much space left to build houses, so the basic question is, if we're going to build there, does this urban development invoke a societal risk problem there? Because we are using the societal risk as a criteria. Currently, two criteria are being used. Individual risk, and we've had several definitions of individual risk already this afternoon, but we look upon it as it's also called locational risk, to make it more clear that it is a risk at a specific location. A risk at a location outside the premises of an establishment, expressed as the likelihood per year that a person that is continuously over there without any protection is killed as a consequence of an event inside that establishment. Societal risk goes beyond that and is the cumulative probability per year that at least 10, 100 or 1,000 people will be killed as a direct result of the presence within the impact area of an establishment. Note that this establishment can be an installation, but can also be an activity, a transport activity. Within our country, with a lot of transport going on, pipelines, railroad, road transport, that is an important fact to take into consideration. So we have strict regulation on what we call external safety. And external applies to, it is offsite. It's not within the premises of your company. No, it's outside. It's a risk that is invoked outside the borders to people who are there. Individual, also locational risk. It is a value that you can calculate on specific spots and is presented on a map by connecting the points with an equal value, and that gives you ISO risk contours. Basically, you can draw contours for different values of this individual risk, and the requirement within the Netherlands is that you have no vulnerable objects within the 10 to the minus 6 contour. Be aware this is based on the unprotected situation. So somebody is there the whole year, standing outside without any protection, no clothes, so heat radiation has full effect. But it's a strict rule. It's a strict rule in the Netherlands. You cannot build within the 10 to the minus 6. And the consequence of that is that authorities are really drawing lines. We've had a mayor of a city who draws a line and said, there's the 10 to the minus 6, and on the other side of the street, I'm going to build a retirement home. That's the way they are using it. So that's the downside of the situation. Fortunately, there is another criteria which gives a penalty for the situation that you are going to build directly beyond the 10 to the minus 6, and that's the societal risk. The societal risk is a two-dimensional graph that presents the size of the group versus the probability of a group of that size will die. In order to judge whether you are on the right side or the wrong side, we are using two indicative guide values. Those are the lines over here. We have two values, one for stationary installations and another one which is for transport situation. It's for the Dutch situation is a bit different from the graphs you saw in earlier session from the UK. The slope here is -2. For the UK it's -1. So it's more strict. And some other countries have other rules, like Belgium, they cut off at 1,000 people. You cannot have more than 1,000 people, even if it's 10 to the minus 12 or something like that. So different ways for different countries. We use those two values. But it's not a strict rule. It's a guide value, and as soon as you are exceeding this line, you have to give a motivation. You have to give a commitment and show that you have an evacuation plan, you have an emergency response plan, and you can use that to get rid of the authorities and say, okay, I have prepared myself for the situation. I'm aware of the fact that I have a bit higher societal risk. But be aware, the societal risk is a two-dimensional graph, and it's calculated by using geographically oriented information about population. You need population distribution, so exactly the location, where are the people living, and you need geographic information about where are my scenarios. You mix them together, combine them, shake them, and there we have a two-dimensional graph which just tells you you're right or you're wrong. That's hardly usable if you are going to determine whether you can build somewhere. It will say, okay, I'm right or I'm wrong, but it is very difficult to comprehend also by local authorities and land use planners. Where is this problem? Why is this problem occurring? Which areas are available for development? So for having this identified, and this situation often occurs, one wants to build and the curve says you can't. And everybody's asking, why not? What's going on there? But where can I build? So you need to have answers that go beyond this two-dimensional graph. So it was identified that we needed a way to present societal risk on a map. Land use planners are always talking with maps. They can illustrate and thinking in maps, geographically oriented information. So the Dutch authorities asked us to develop a method to present societal risk as a firm criteria on a map. But that leads to some requirements, because why are we doing this? You want to know which population is contributing to the risk. That was a question that was often raised. Are there areas that already have a societal risk problem? What is the extent of the problem? Is it a large area? Is it a small area? And which areas are safer or less affected and provide possibilities for urban development? But most of all, nobody wanted yet another criteria. The rules are strict enough as they are. It's just a visualization method. The first approach was basically very simple, straightforward. Individual risk, the contours, they are based on two-dimensional, on geographic information. You have for every spot, for every location, you have a value of your individual risk. Why not simply multiply that with the number of people who are at that spot? That will give you an indication of the potential loss of life that you have for that spot. It can be achieved with a simple post-processing using standardized GIS tools by simply multiply two spatially distributed grids. So that gives you an illustration where every cell has a PLL, potential loss of life value, that you can illustrate with a color. And that led to illustrations like this. This is Rotterdam Harbor area with some chemical storage over here, and typical ISO risk contours, the 10 to the minus 5, 6, 7, minus 8. And this clearly indicates the population that is affected and the amount of population which is there. However, this map has got nothing to do with societal risk, because individual risk is based on unprotected, outside, 100% of the time over there, whereas societal risk includes vulnerability, effectiveness by staying inside, and the effect of clothing that reduces your vulnerability for heat radiation. For toxic scenarios, if you stay inside, the lethality is much lower, and that is taken into account in societal risk calculation. So this map gives a clear overestimation of the risk and has nothing to do with the societal risk which we want. So we went beyond this phase and decided to use a more elaborated method and use the standardized, and you can call it purple book, but you can find the same method in other publications on how to calculate a societal risk. So you work with locations and frequencies, but include the values for lethality inside and outside. So you make that difference between protected and unprotected situation. Use the wind and weather definition, so the probabilities of wind occurring. You perform the complete calculation, but instead of accumulating all those values into one FN curve by counting frequencies and number of victims, we store those results for every grid cell. Not accumulate all, but remember them for every grid cell. And eventually, that gives you an FN curve per grid cell, per cell of your study area. So the number of victims, or lethal response fraction, and frequencies for every event that may hit that cell are stored and combined. Then eventually you end up with an event curve per location. To give you an idea, a map of a city, gridded population, so these cells are all taken into account. And suppose you have a toxic event that can be there, which has a possibility of this event being in this direction, so it has to do with the probability of the wind being in that direction. And you count the number of fatalities for every grid cell and store them for every location. This area, it can be hit by a toxic scenario. Suppose you can have another scenario which involves a propane disaster, a Blevy phenomena, with typical lethality footprints. So you have a number of victims for every cell which is under the footprint of this event. You can have another event in the center, or an explosion event. And some areas may be hit by different events. If you have different installations on your site, you have a vessel in the north side and a south side, and another one in another place, you're looking at the risk that is affecting a specific cell. So for every cell, we store the possibility of this event hitting the cell and the number of victims that are hit. That eventually, the number, because this is not the Dutch windmill, this is an illustration of the fact that you have to take into account that an event can happen for different situations, for different wind direction. Somebody can get hit by wind coming from north, or a bit changing wind, and of course you have also different stability classes. If you have very stable weather, the toxic plume may be much larger. Eventually you end up with an FN curve per grid cell, and that grid cell and that FN curve can be translated to a color. Basically you have a two-dimensional information on every cell. By taking the surface beneath the FN curve, often referred as the expected value, by taking this value and using this value as an indication of the societal risk over there, you get a societal risk map where every color corresponds to a specific expected value. And this is a true representation of the societal risk that is happening on this cell. It gives an illustration of the contribution of this cell to your societal risk. And it just illustrates hotspots or possible problem-causing habitation. Another way to use the same kind of information is not store the number of victims per cell, but use the total number of victims that are occurring for the situation that wind is in this direction. And instead of storing the individual number of victims per cell, we use the total affected group, and this cell takes part of an event that has 200 victims. So again, for every event, the total number of victims that occurred for the scenario that was hitting the cell are stored. Combined with the frequency, eventually you end up with a FN curve per cell, but this is the total societal risk. This is really the societal risk of the scenarios that are affecting this location. This gives a totally different map. The same area, but now another illustration. It gives a clear view of the order of magnitude and the total extent of the societal risk. It illustrates if there's a problem and where there's a problem. We have a societal risk curve for every cell, but it's translated into a color by using the distance to the guide value. We have a guide value over here. Basically, the color turns red if I'm above the guide value, and if I'm beyond, I will get more green and eventually blue. So it's a gradient coloring that illustrates the space you have left before you are exceeding the guide value. So two different societal risk maps, the area map and the contribution map. The first, this one gives an indication which areas are affected and presents the level of the risk. Here you can see now we are using only 6 colors to make a more distinct leveling. You can see red is really wrong. Orange is a factor 10 beyond. Green is a factor of 100 beyond. But it gives an illustration of how much you are exceeding or going beyond the societal risk, whereas the other one gives an illustration of the amount that this cell is contributing to the societal risk. Having developed this method, we have used it in an Eimond case study. In this area we have a fertilizer plant here, we have a steel industry, we have LPG filling station and LPG transport. Again, the 6 color scale. This map, although everyone was concerned about the chemical side and the fertilizer plant with ammonia scenarios and toxic scenarios, which would reach very far, it appeared that the LPG scenarios were the ones that were really creating the problems. The typical circles are Blevy footprints for LPG events. And it clearly created a growing understanding of this spatial distribution of societal risk. And in this case, it was decided to reroute the LPG transportation lines because that gave too high risk. This is a terrible red illustration of Rotterdam Harbor Rotterdam Harbor again, but now with road transport, some high pressure gas lines. In this case, the question was, can we have some additional population close to dangerous activities? Do we increase the risk considerably? But it was very clear that in this case, very toxic transports here in the south were affecting a large area of the Rotterdam habitated area. And the insights from this map triggered a lot of interesting discussions between authorities, risk experts, and spatial planners. Terneuzen study with a large ammonia production site, bromide storage. Here we have a lot of gas pipelines, road transportation, and again we had a large red area with exceeding the societal risk guide value. But these maps triggered fascinating debates about, is it correct to accumulate risk coming from more than one source, and in this case from more than one pipeline, even if they were in the same lane. One is used to take only the owner of the creator as responsible. Again, a lot of insight was created here. Currently, the method is available in software, and it's possible to accumulate or look at separate situations. You can make selections for scenarios. You can make very fast evaluations of alternative development plans. You can say, well, what happens if I add population? Will the values increase and is it allowed? You can look at temporary population, change the transport and intensity or failure rates for scenarios, and possibly evaluate the change of routes. Here an illustration of a large chemical site in the south of the Netherlands where we have an ammonia plant, acrylic ACN, and we added, there were plans for urban development here, and it clearly indicated, well, you get an area here with exceeding the guide values. Of course, the same effect can be illustrated in conventional graphs, but now you can see the area, the affected area, the size of the area, and the amount of the problem. You can make sheets for or presentations for separate sources, several contributions. Evaluate the change in transport intensity, so change the intensity, and you can see that the maps, the colors get lower and it's more allowed. So eventually we can say, well, the societal risk maps have proven their value because it gives you more insight, and even non-specialists can clearly see what's going on. Typical applications for contribution map is guiding for emergency response planning or pinpointing areas for redevelopment or reallocation of population. For societal risk area map, guiding urban development planning or pinpointing safety problems to non-specialists. So it's really in risk communication as well. So we are looking from the point of the receiver. It appeals, but be aware it's not obligatory. Also, it appeared that you still need experts to explain what's going on and what is causing the risk, and whether it's toxic or flammable situations. Spatial planners would often simply ask, okay, which color is a problem? Whereas safety specialists will always ask, okay, but what do I see? What's behind those colors? It's a visualization and it's not a criteria. So the traditional societal risk graphs are still required. It's a supplementary view just to get more insights. And be aware the individual risk contours still provide the first step where not to build, not inside the 10 to the minus 6. So we can say we have quantitative risk analysis applicable for urban planning decision support. This is a conclusion that is basically beyond what we have told, but what's important is that societal risk maps will be provided in the new risk curves version. Okay, thank you for your attention.